March 15, 2018. Miami, Florida, 1:46 p.m. A 175-foot concrete bridge collapses onto 6 lanes of live traffic. 8 cars are crushed. 6 people die. The bridge was 5 days old. It was built to solve a simple problem. Florida International University sits on one side of a busy 8-lane highway. A student neighborhood sits on the other side. Students cross that road every day. Some got hit by cars. The university spent $14.2 million to fix that. They built a bridge, a fast one, a modern one. 5 days later, it killed the people it was built to protect. 3 companies built this bridge. Fig Bridge Engineers designed it. MCM, Munilla Construction Management, built it. Louis Berger reviewed the design to make sure it was safe. 3 companies, 3 sets of experts, dozens of engineers between them. None of them stopped what was coming. The bridge was funded by the U.S. Department of Transportation, $19.4 million in federal grants. It was part of the University City Prosperity Project, a government initiative to make the area safer and more connected. FIU was proud of it. They announced it publicly. They called it innovative. The bridge was designed to last more than 100 years. It was designed to survive a Category 5 hurricane. It did not survive 5 days. The method used to build it was called Accelerated Bridge Construction, ABC. The idea is straightforward. Instead of building a bridge piece by piece over a highway, which means closing lanes for months, you build the entire span somewhere nearby, then you move it into place all at once over a single weekend. Less disruption. Faster construction, a modern solution. The main span of the Florida International University Bridge weighed 862 tons. On March 10, 2018, crews moved it across the road in one carefully coordinated operation. The highway closed briefly. The span was set into position. The road reopened. Engineers and university officials watched it happen. Some of them celebrated. The bridge looked finished. It was not finished. Workers still needed to complete the tension rods running through the bridge's truss, the internal steel rods that helped the structure hold its shape under load. That work was ongoing when the bridge fell. To understand why the bridge collapsed, you need to know one specific spot. Engineers call it Node 1112. A bridge truss is a triangle-based structure. Diagonal members run at angles. Vertical members run straight up and down. They all connect at nodes, the joints where pieces meet. Nodes carry enormous force. They are where stress concentrates. Node 1112 was where a diagonal truss member met the bridge deck at the north end of the span. It was a critical connection. Force from the entire structure funneled through it. FIG's engineers calculated how much force that node would carry. They calculated how strong the concrete at that node was. Both calculations were wrong. They underestimated the load. They overestimated the strength. The node was being crushed by more force than FIG's design said would ever be there, and it was made of weaker concrete than FIG's design said it needed. The bridge was cracking from the inside out before workers ever finished building it. This is where Louis Berger comes in. Peer review exists for exactly this reason. An independent engineer reads the design, checks the math, and looks for mistakes. It is the safety net built into every major engineering project. Louis Berger reviewed FIG's design. They did not catch the calculation errors at node 11 to 12, the net had a hole in it. And the one mistake that mattered most fell right through. After the span was moved into place on March 10, something visible happened. Cracks formed on the north end of the bridge at node 1112. Workers saw them. They photographed them. A senior project manager sent emails with photo attachments, flagging the cracks to the team. The cracks were not small. They were not the kind engineers dismiss as surface-level shrinkage. They were structural. They were the bridge's surface showing what was happening underneath. Workers on site felt urgency. That word, urgency, would later appear in the OSHA investigation report. The people closest to the structure knew something was wrong. FIG did not treat it as urgent. On the morning of March 15th, 5 days after the span was moved into place, a meeting was held. Representatives from Florida International University, the Florida Department of Transportation, MCM, and FIGG sat in a room together. The meeting lasted 2 hours. The FIGG engineer of record gave a presentation about the cracks. He showed the data. He walked the room through his analysis. At the end, he told everyone that the cracks did not compromise the structural integrity of the bridge. He said there were no safety concerns. No one closed the road beneath the bridge. No one halted construction. Workers went back up. The meeting ended at approximately 11:30 a.m. The bridge collapsed at 1:46 p.m. 2 days before all of this, on March 13th, FIGG's lead engineer, W. Denny Pate, had called the Florida Department of Transportation. His contact there was a man named Tom Andres. Pate left a voicemail. He said cracks had appeared on the north end of the span. He said repairs would be needed. Then he said something that would later define the entire tragedy. He said, from a safety perspective, there was no issue. He was not concerned about it. The voicemail sat unheard on Tom Andres' landline for 2 days. Andres was out of the office on assignment. He did not hear the message until the day after the bridge collapsed. NTSB records later revealed there was a second voicemail as well. Andres confirmed he did not listen to either one until after 6 people were already dead. At 1:46 p.m. on March 15th, workers were on top of the bridge tightening tension rods. They were working directly at node 11 and 12, the exact point where the concrete had been cracking. The additional force from that adjustment was the last load the node could not carry. The bridge came down in seconds. 8 cars were crushed beneath 862 tons of concrete. Emergency responders arrived within minutes. 14 police units responded with 33 officers, a rescue operation that quickly became a recovery operation. 6 people died. 1 was a construction worker on top of the bridge. 5 were motorists sitting in their cars at a traffic light below. Their names were Alberto Arias, 53, Brandon Brownfield, 39, Alexa Duran, 18, Rolando Fraga, 60, and Oswaldo Gonzalez, 57, Fraga's partner, sitting in the same car. Alexa Duran was an FIU student. She was 18 years old. She was crossing the road the bridge was built so students would never have to cross again. 4 more people were seriously injured. 1 construction worker was permanently disabled. 3 separate investigations launched immediately. The National Transportation Safety Board, NTSB, OSHA, local law enforcement. The NTSB conclusion was direct. Load and capacity calculation errors made by FIGG bridge engineers were the probable cause of the collapse. Louis Berger's peer review failed to catch those errors. The FIGG engineer of record failed to recognize the significance of the cracking at node 1112. He failed to bring in an independent reviewer before authorizing work to continue. OSHA cited 5 companies: FIGG, MCM, Bolton Perez and Associates, Structural Technologies, and the Structural Group of South Florida. 7 violations in total. Combined penalties were $86,658. $86,000 for 6 deaths. The Miami-Dade District Attorney's Office opened a criminal investigation into negligence. The road beneath the bridge had stayed open despite visible, documented, photographed cracking. Workers had expressed urgency. A meeting had been held and dismissed. No one closed the road. Prosecutors ultimately did not file charges. Establishing criminal liability in complex engineering cases is difficult. The law does not always reach as far as the consequences do. MCM, the construction company, did not survive the aftermath. Legal costs and settlements pushed it into bankruptcy. It changed its name and dissolved. FIGG bridge engineers did not recover either. Their reputation collapsed alongside the bridge. They were excluded from future projects. The families of the victims filed civil lawsuits. They settled for $102.7 million. No dollar amount gives Alexa Duran's father his daughter back. He told reporters she was trapped in her car and could not get out. The NTSB published its final report. It made clear what needed to change. Peer reviews must be conducted at every phase of design and construction, not just at the beginning. When structural cracking is observed, work stops and the road closes until an independent expert signs off. No exceptions. No meetings where an engineer reassures a room and everyone goes back to work. The system that was supposed to catch Figg's errors had one layer, one reviewer, one check. That reviewer missed the most important calculation in the entire design. A bridge over a live highway needs more than one set of eyes. It needed more than one chance to catch a mistake. It got one. It failed. And 6 people on a Thursday afternoon in Miami paid for it. 6 people left home on March 15, 2018. None of them knew a bridge above them was cracking. 3 chances to stop it. The voicemail, the emails, the morning meeting. Every single one was dismissed. The bridge was designed to last 100 years. Engineers celebrated when it was moved into place. A university put out press releases. 5 days later, a father stood outside a hospital telling reporters his 18-year-old daughter was trapped in her car and could not get out. The bridge was built to save lives. That was never the hard part. The hard part was admitting it was not safe.